in the last lecture, we have seen the pipeline structure for the MIPS32 processor. You may say that it is an ideal pipeline, like we have not considered many of the real problems or conflicts that can arise and cause the so called hazards during instruction executions in the pipeline. So, from this lecture onwards, for the next few lectures, we shall be looking at these kinds of conflicts or hazards that can impact or degrade the performance on a pipeline to a great extent, and what are the approaches we can use or follow to avoid such degradations to the extent possible. So, we start our discussion on pipeline hazards in this lecture. So, let us try to first understand what is a pipeline hazard. So, we have seen an ideal pipeline. Okay. So, an instruction pipeline in the ideal sense should complete the execution of one instruction every clock cycle. That is how a pipeline works. But when we say there is a hazard, it means some kind of a scenario or some occurrence of some events, because of which we cannot operate the pipeline at its maximum possible speed. Because you see, there are several instructions which have entered the pipe already. Several instructions are in various stages of execution. There can be some dependencies between the instructions. They may be trying to access some common resources, because of which there can be a conflict. Because of branch instructions, I have said earlier, we may have to wait till we know the outcome of the branch and the target address. There are several such instances which may prevent a pipeline to work with its maximum possible capability or speed. So, loosely speaking, such situations are called hazards. They prevent a pipeline from operating at its maximum possible clock speed. So, which means that we cannot feed an instruction every clock cycle. So, such hazards can prevent some instructions from executing during its designated clock cycle. Means, suppose an instruction was supposed to be entering the pipeline now, but maybe I will have to make it wait for one clock cycle and make it enter the pipeline in the next cycle. That is what is meant by this. Broadly speaking, hazards can be classified into three types: structural, data and control. Structural hazard, these arise due to resource conflicts. Well, like one example we have already seen, like in the memory access, instruction fetch IF and mem. Two instructions may be trying to access instructions and data. That is some kind of a structural hazard. If there was a single memory module, then one of the instructions would have to wait, but because we have used separate instruction and data caches, they can proceed together. So, we have avoided it. Data hazard, they arise because of data dependencies between instructions. Say one instruction is producing a result, maybe the next instruction is using that, such dependencies. And control hazard, they arise due to branch and other instructions like interrupts, let us say, that changes the program counter. Right. So, what happens when such hazards show up? Well, there are several alternate strategies, we shall be looking at some of them. Well, we can use some special hardware to detect the hazard, some control circuits. So, to detect the hazards whenever they appear, and to try and avoid the conflict. Okay. This is one alternative, so that some hardware will be there, so which will be trying to detect such situations which can result in hazard and try to overcome them automatically. But as an alternative, we can simply insert stall cycles without using special hardware. This is a cheaper alternative. Like, suppose I find that there is an hazard. So, if I allow the next instruction to enter the pipe, there will be a clash somewhere. So, I hold the instruction back, maybe I feed it in the next clock, not in the present clock. If I do that, I say that I am inserting a stall cycle. For one cycle, I am not feeding anything in the pipeline, I am stalling the pipeline for one cycle, and then again I am feeding the next instruction after that. Then the hazard will not show up. This is one simple strategy. But if I follow this principle, suppose I stall one instruction, then all the instructions that follows this particular instruction obviously will also get stalled, because unless this instruction enters the pipe, those instructions will not be able to enter the pipe also. And depending on the criticality of the hazard, we shall be seeing the various situations, number of stall cycles can vary. Okay. And the important thing to note is that whenever we are inserting stall cycles like this, so the understanding is that the instructions which have already entered the pipeline and are in the process of execution, they can proceed normally, there is no problem. But I am holding back the instructions that are following, I am inserting one or more stall cycles. So, they will be delayed. After the stall cycles, they will be fed into the pipeline. Okay. So, this is what I just now said, instruction before the stalled instruction can continue, but no new instructions can be fetched during the duration of the stall. Now, as I had said, for example, in this strategy, we may have to insert such stall cycles, and this kind of hazards will result in performance degradation, because we are not allowing instructions to be fed or entering the pipe in every clock cycle. That is why we are not able to get the full pipeline performance that is possible in the ideal case. Okay. Fine. So, let us make a simple calculation. So, with respect to a non-pipelined version, suppose we are trying to estimate the speed up in a pipeline. So, a simple measure of speed up is to divide the execution time of the non-pipeline version with the execution time of the pipeline version. So, how I can calculate these execution times? So, one simple way will be to multiply the cycles per instruction of the non-pipelined version with the clock cycle time of the non-pipelined version, assuming that the number of instructions are the same in both the cases. Similarly, for the pipeline version, CPI for the pipeline version multiplied by the clock cycle time of the pipeline version. So, I can separate these out, the clock cycle times and the CPIs. Now, when we talk about pipelining, well, we can either say that we are trying to reduce the CPI, or we can argue that we are trying to reduce C, but actually reducing C is not true, because we are not really reducing the clock cycle time, but you can argue in some way, like you can argue in some way, means you can say that in a non-pipeline version you had the whole computation as a block. So, as if your clock was running, let us say 5 times slower, but now by making a pipeline with 5 stages, you are making the clock run 5 times faster. That may be one argument, okay. But a better argument may be that we will be following here, that well, we are not saying that we are making clock faster, but we are saying we are making CPI smaller, cycles per instruction smaller. So, means you can argue in either way, okay. So, now another thing is that the ideal CPI, so in the absence of any hazards, will be equal to the CPI of the non-pipelined version divided by pipeline depth. Pipeline depth means number of stages in the pipeline. Now, in our example, for the MIPS example, pipeline depth was 5. So, in the ideal case we are getting a speed up of 5. So, CPI was reducing by 5 times. So, just you can substitute the CPI no pipe expression here, and this expression becomes speed up equal to C no pipe by pipe. Instead of CPI no pipe, you write ideal CPI multiply by pipeline depth, this expression, right. So, this is one way you can write it. Fine. Now, suppose we are using the method of inserting stall cycles for removing hazards, for avoiding hazards. So, we can write the actual CPI of the pipeline. Say actual CPI of the pipeline will obviously be greater than the ideal CPI. It will be ideal CPI plus average pipeline stall cycles per instruction. This will be the impact of the hazard on the average case. So, your CPI pipe you can write like this. So, this expression which you got, the CPI pipe you can substitute there. So, you can write instead of CPI pipe this ideal CPI plus pipeline stall cycles per instruction. Okay. So, if you ignore the difference in the clock cycle time of the pipeline and non-pipeline version, of course, as you know that because of the latch delays this C pipe is a little larger, but if you ignore that, just if we assume that these are equal, so you are left with this part, speed up equal to ideal CPI multiply pipeline depth plus ideal CPI plus pipeline stall cycles per instruction. So, this is an expression which you can use to estimate the speed up for a pipeline in presence of stall cycles, right. So, just remember this expression. So, we shall be using this later in some examples. Let us look at the hazards now one by one. Structural hazards to start with, we said that they arise due to resource conflicts. See, if I have a single copy of a resource and 2 instructions or 2 stages, they are trying to use the same resource. So, we have seen 2 examples, one is for a memory and the other is for the register banks, read and write. The ID stage is trying to read from register, WB stage is trying to write into a register. These are examples of structural hazards, right. So, if the hardware does not support concurrent or overlapped execution, then structural hazards will show up. So, these 2 examples already we have seen, I have again mentioned it. Single memory to store instruction and data. If we have a single L1 cache, not separate instruction and data, then when an instruction is being fetched and some other instruction is trying to read or write, the next instruction will have to wait. So, you have to insert a stall cycle. Similarly, an instruction is trying to read data from the register bank, while some instruction is trying to write a register. So, again, if you do not follow that principle I mentioned earlier, that you do write in the first half of the clock and read in the second half of the clock, then the instruction that is trying to read data will have to wait. You will have to insert stall cycles in that case. So, you see that if you do not take precautions or put in some additional hardware to detect and avoid this kind of a hazard, your stall cycles will get inserted automatically. Otherwise, your instruction execution process will not be correct, right. And another example I am giving, say let us say some of the functional units like floating point add or multiply, they are not fully pipelined, and suppose there are two instructions one by one consecutive, they are trying to use floating point add or floating point multiply. Because they are typically instructions that consume more than one cycles, they will result in stall cycles, because when say the first instruction is doing multiply, they will be using multiple clock cycle during the EX stage, because multiply cannot finish in one cycle. Okay. So, it is consuming the EX stage for more than one cycle. So, if the next instruction is also requiring floating point multiplication, next instruction will have to wait, you will have to insert stall cycles. Okay. These are some examples of structural hazards. So, let us take some examples. Let us say we have a single port memory system, that means I have a single memory system that stores both instruction and data. I do not have separate instruction cache and data cache. Okay. And I have an example sequence of instruction. Let us say I have a load followed by a sequence of arithmetic and logic instructions. So, in the ideal case, instruction execution will proceed like this, but as I had said, this load instruction will be trying to access memory here, do a load, and this AND instruction will try to do the instruction fetch here in IF, right. So, this will be a clash, this will be a structural hazard. So, suppose we have not replicated the memory. So, what is the solution? I can insert a stall cycle here. So, the control circuit, the hardware will automatically detect that there is a conflict. This instruction is trying to access memory, this was a load instruction. So, you cannot do an instruction fetch here. So, it will automatically insert a stall cycle and it will resume the instruction fetch in the next cycle. So, the instructions that follow, they will also incur a one cycle delay. Okay. That is what I said, that you stall an instruction and all instructions that follow, they will also be stalled by that equal number of cycles. Okay. Fine. So, here we show that how we can insert a stall cycle to eliminate this structural hazard. Now, let us work out an simple example. So, we consider an instruction pipeline where data references constitute 35% of the instruction, which means load and stores. So, out of all instructions, 35% are load and stores, and ideal CPI, well, ignoring structural hazard, is 1.3. So, now the question is, how much faster will be the ideal machine without the memory structural hazard? That means without hazard means I have already replicated I cache and D cache, let us say. versus the machine with the hazard, that means a single integrated memory that stores both instruction and data. So, we use this expression that we worked out earlier. So, how we do it? For the ideal machine, the ideal CPI is 1.3, ideal CPI is 1.3, and for the ideal machine there is no structural hazard. So, pipeline stall cycles per instruction will be 0, right. And for the real machine, what will happen? For all such data reference instruction, there will be 1 cycle delay because of the stall. So, ideal CPI is 1.3 and pipeline stall cycle per instruction, it will happen 35% of the time, and for each of that case there will be 1 stall cycles inserted. Okay. So, if you just calculate this speed up, this becomes 1.6, this is actually cancels out, this is 1.65 by 1.3, it is 1.27. So, the ideal machine is 1.27 times faster than the real machine. So, this means that in reality, whenever you have this kind of hazards, your performance degrades. There will be about a 27% degradation in the performance. Now, the question is, why can't we remove structural hazards by inserting additional hardware, since it is so important? If there is a structural hazard, the performance drops. So, why can't we invest more? The question is, how much is the cost to replicate the hardware? There are a few things like, for example, iCache and Dcache, as I said in the example. This you can possibly do without much increase in cost, but there are a few things which you possibly cannot replicate. So, to reduce cost of implementation, sometimes structural hazards remain in certain cases. For instance, pipelining all the functional units may be too costly. For instance, the divider, say the addition and subtraction and multiplication are relatively easier to implement in a pipeline, but division is not, division is more difficult, right. So, that may be a case. And third thing is that you can bank on Amadel's law again. You see that how frequently such structural hazard scenarios occur. If you see that such structural hazards are not that frequent, then you may avoid the effort and cost for those. You will see that, well, I find that division, floating point division in a program appears very rarely. So, let me not invest anything to improve that, to remove that hazard, let that hazard remain. So, whenever there is a floating point division followed by another division, let stall cycles be inserted. But for most of the scenarios, such occurrences will not happen. Okay. So, we are trying to make the common case fast, okay, right. But because memory access structural hazard is very frequent, we replicate the hardware, because this is something we cannot compromise. Because if we use a single integrated cache, for every memory access we may have to use a 1 stall cycle, that is too expensive. Okay. Fine. Now, let us come to data hazards. Data hazard means there is some dependency among the instructions. Let us say I have an add instruction which produces a result in R2. There is a following instruction which uses the value of R2. So, unless you take proper precaution, you see normally what happens? Normally this add instruction will be writing the value of R2 in WB, write back stage, and subtract instruction will be prefetching all register operands in ID. So, it is trying to prefetch before the value has been written. So, if you do not take proper precaution, the subtract instruction can fetch the old value of R2, not the latest one, okay? Because R2 is written here and you are trying to read R2 in the ID phase here, it is earlier in time. This is what data hazard means. Okay? So, apparently what it means, what it shows is that you possibly have to insert 2 or more stall cycles, because unless WB is complete you cannot use ID. Maybe this ID you have to shift here. See, register read write you can do parallelly, but at least you will have to shift it here, right. But you will see that we can do better. A NAPE solution is by inserting stall cycles, like is that after this subtraction is decoded, we see that here also we are using R2, same operand as the previous one. So, we will be waiting till WB is completed, insert stall cycles. So, in the NAVE implementation 3 clock cycles, stall cycles will be used, like this add, this subtraction is fetched, it is decoded. So, while decoding you find out that well R2 is here and already the earlier instruction has R2 as target. So, now you will have to use 3 stall, this will be converted into a stall, again 2 more stall, you will have to repeat ID again here. So, all subsequent instructions will be facing those stalls, right. So, they will all be delayed. So, 3 clock cycles are wasted, but fortunately because of the simplicity of the instruction set we can reduce the number of stall cycles. So, how we can do that? Well, we shall explore 2 methods. One is called data forwarding or bypassing, and the second one we have already seen, concurrent register access, this we have already seen. So, we are splitting a clock cycle into 2 halves, register writing is done in the first half and reading in the second half, this we have already seen. Okay? But the second one is data forwarding and bypassing. The idea is very simple. See, the first instruction which was generating the result, that R2, was writing the result in WB, but if you look at the instruction execution process, the value of the result was already calculated at the end of EX, because suppose it is an add instruction, the actual addition is carried out during EX, right, but the value is written to the register in WB. So, if we take the output of the ALU directly, which is already calculated, and by using some additional multiplexer you forward that value to the next instruction whenever it needs it. So, maybe you will not have to wait for the WB stage, you may get the value earlier. This is called data forwarding or bypassing. By using additional hardware consisting of multiplexers, the data required can be forwarded as soon as they are computed, instead of waiting for the result to be written into the register. Okay? Fine. So, bypassing, what is the idea then? Just as I have said that the result computed by the previous instruction is stored in some register, it is the just output of the ALU, there is a register ALU out, you recall. So, the value is there. So, you take the value directly from there, do not wait till WB and forward it to the instruction that require the result. So, to do this you need some additional connections, data transfer paths and some additional multiplexers. So, your control circuit also becomes a little complex. It will have to analyze the source and destination registers of the consecutive instructions, and it will automatically means activate or deactivate this kind of forwarding paths whenever required, right. So, let us see let us take an example here which shows lot of data dependency, like this add instruction generates R4, this R4 is used in all consecutive 4 instructions. Okay. So, there is a data dependency in all. So, WB so in the normal case the result will be written in WB, but these instructions are trying to read them here, here and here. So, first instruction computes R4, which is required by all the subsequent 3 instructions. The dependencies are shown here, but the last instruction, of course, it is using ID after WB. So, it is not affected. So, it is only the 3 consecutive instructions which need to be looked at. Then, so now you see this AND instruction, we have already solved this by splitting the register access. We are saying writing is done in the first half of the clock cycle and reading is done in the second half of the clock cycle. So, this conflict is already resolved. So, actually we are left with these 2 conflicts. But one thing you see, it is possible to remove these 2 conflicts also. Why? Because the first instruction is calculating R4 in the EX stage, right, the result. The result is available here. So, you need not have to wait till WB to be written into R4. You can directly take from here and forward it to the EX stage here, where the subtract will be requiring it, this add will be requiring it. So, from here you can forward it here or you can forward it here. Okay. The idea is this. So, data forwarding means the value of R4 is actually getting calculated here and you are forwarding the value like this. But as I have said is that you need to forward only to the 2 consecutive instruction, you do means you really do not need beyond that, right. So, we need to forward the result directly from the output of the ALU in the EX stage to the appropriate ALU register of the following instruction. So, when the next instruction enter the EX stage, this instruction will already be in the MEM stage. So, from there the result has to be fed back to the input. Okay. So, something like that. So, how we can do that? By using some multiplexer and additional paths. And this already we have said earlier. So, by splitting register read write we have already avoided or reduced one dependency. So, in the NAVE forwarding there was the requirement of forwarding 3 instruction, but if you split register read write we reduce it to 2. Okay. This we have already discussed earlier in detail, right. So, this I am skipping. So, because of this register splitting thing, this conflict has been avoided. This is what I am saying, by in a clock cycle by using write in the first half and read in the second half, this conflict we have already avoided. So, in the clock cycle write here, read here. So, there is no conflict. But for the others, this is the forwarding hardware we require. This is the EX stage, this is the ALU where the actual calculation is done. Normally, the data input of the ALU is coming from the earlier stage, but because of the forwarding, we use some additional connections from this ALU out from here either to this in, because we do not know that which operand will be requiring this, maybe the first operand or the second operand. Similarly, if there is a dependency of the second most instruction, the instruction will already be moved here. So, this ALU out is copied here, this value also is getting fed back here or here. Well, here I am showing another feedback path also. This will have required, this will be required for load instruction, but in the example you have not seen this yet, but this is the complete forwarding hardware. So, for load instruction data will be read into the LMD, this LMD value is also forwarded. Okay. So, you see basically you need some additional inputs to the multiplexer. Earlier it was a 2 to 1 mux, now it has become a 5 to 1 mux. Okay. This is the this is forwarding hardware which I am talking about. So, the first instruction which generates the result, maybe it has come here, now that partial result is here, the next instruction has come here and is trying to use that result, you forward it from here, or the instruction generating the result has come here, the next to next instruction has reached here. So, you forward it from here, here ALU out, just like that. So, all possible paths are shown. So, either you forward it from ALU out here, or for load instruction from LMD also there is a path. Okay. So, with this we come to the end of this lecture. What we have seen here is that we had seen the importance of handling and tackling hazards, because they can cause a very significant degradation in performance. We had looked at structural hazards and mentioned that structural hazards can be avoided by replicating resources, no other way out. So, wherever possible you can replicate. Then you looked at data hazards. Data hazards are important, and apparently without anything you are requiring 3 stall cycles for at least the ALU instructions with data hazards. But what we saw is that using forwarding hardware and by splitting the register access, we are able to totally eliminate data hazard related stalls for ALU instructions. In the next lecture, we shall see that what will happen if there is a data hazard for a load followed by an ALU instruction which uses the loaded value. So, there we shall see that it is not possible to totally eliminate the stall cycle, but we can try to reduce it again. So, this we shall discuss in the next lecture.